right, well then let's begin. Hello everyone, welcome back to Physical Geology 1403. Gavin, would you grab the door for me? Thank you. Okay, so lecture 10. We're trucking right along. There's actually only 3 lectures left after today, guys. No, 3 lectures. There are also a few exam reviews. Okay, so bear that in mind. Your next exam is going to be after lecture 11. So we're getting lecture 10 today, lecture 11 on Thursday, if you're watching this currently. Yes, you'll get your exam review the following Tuesday, unless, and we can discuss this after class, there is an option to get an exam review on Thursday after lecture instead of having lab time, depending on whether you guys need lab time. So you can have the exam this coming weekend or take it during the week, next week. So we're at a place, we're doing well. We haven't had a holiday this term where I've had to miss a day of class. So I'm not behind. We're on schedule. So we have a little bit of flexibility there. Huh? What was that? Nothing? Okay. Okay. So that is an option. Chew on it today. Let me know at the end of class what you guys would prefer. And we can just go a little bit long on Thursday, the next time we meet, and have an exam review immediately following the lecture. And you can have all weekend to take the exam. Or we can have our exam review on Tuesday next week, and you have to take the exam either Tuesday or Wednesday. Before Thursday is the point. Okay? Chew on that. Let me know. Any questions or comments or cool stories or anything? Yeah.
We'll vote for either if we want to do it during the week or on the weekend.
Yeah, we'll vote. Remind me after class and we'll hold a vote. Online students, I'm sorry, you can't vote. You're not watching this or participating live, so it'll be up to these students here. Class movie night. Let me see what the results for that were, because that's coming up. I think that's a week from this Friday. It's going to be Friday, October 3rd.
Oh, 3rd.
Yes, October 3rd. So a week from this Friday. You guys okay over there? All right. The results. Drum roll, please. I love you guys. All right. San Andreas is the winner.
Yippee!
With 41.3% of the vote. And 100% of you voted for October 3rd. Oh, well, look at that. Unanimous. It was the only option I gave you. So, yeah. All right, so October 3rd, 6 p.m., probably in this room, because the projector's actually been behaving. It hasn't been flashing on and off during class. So I'm hoping it will keep that behavior up. And this room has better speakers than that room. So we'll probably be in this room. And yeah.
Is that extra credit going to be like the same where it goes to the lowest exam?
Yes, all extra credit is applied to the lowest exam. Okay. So you'll get a little extra credit from completing the assignment associated with watching the movie. Now, if you cannot make it to that movie night, it's always fun if you can make it, right? But if you cannot make it, you'll need to get access to that movie on your own. I can get access to that movie through a streaming service. I can purchase it, I can rent it, whatever we need, as long as it's a class activity. But I cannot broadcast it. So online students, I'm sorry, you'll have to come here in person or access the movie yourself to complete the assignment. The extra credit assignment, again, this is extra credit. It is not required, okay? So you'll watch the movie, you'll complete the assignment. I usually hang out for a few minutes after the movie. If you guys have questions about the assignment, we can discuss it right afterward. My oldest, my 7-year-old son, he'll probably join us for that. Sometimes my 5-year-old daughter does too. So we'll see what's going on that night. But yeah, Friday, October 3rd, 1 week from this Friday. So what is that, 10 days away? Wednesday, Thursday, Friday, 8 days away. No, 9 days away. Huh, I know math. Okay. Any questions? Great. Then let's get back to our lesson and turn this back on. Alrighty. Yep, we are rolling. All right. Questions, other fun stories, interesting things that you heard / learned or that you want to share with the class? Huh? Anything cool? Yeah.
How come it's like very hot at like how come like deserts are very hot during the day, but can be like very very cold at the night? Wouldn't they so be like there?
What a very relevant question. Why are deserts so hot during the day and so cold at night? Wouldn't they still be hot during the night because they were so hot during the day? Great question. Something we're actually going to talk about today, but you already have some of the information for explaining. We talked about this when we learned about the characteristics of water last week.
Because it collects energy, right?
What does?
Sand. Are the water in the sand?
No, not the water in the sand. If there was a lot of water in the sand, it wouldn't really be a desert.
Oh, yeah.
Yeah. No, that's okay. There are no stupid answers. Okay, don't test that. All right.
Is it the winds that carries the sand, like kind of cools it down?
No. So, again, this is something that we'll talk about today. But what I've already shared with you when we learned about glaciers and the properties of water is that water holds heat a lot longer than the land does. The land gets it quick and loses it quick relative to the water, right?
And since there's not any water or that much water in the desert,
Yeah. There's not much water on the surface. There's not much water in the air, and therefore heat comes and goes quickly. Heats up fast, cools off quick. Okay. Again, a concept we're going to discuss today.
That's why Florida is so hot.
Yeah, Florida is very humid. It's very hot. Same thing with Hawaii. I lived in Hawaii for 3 years. I can't remember a single day that wasn't hot. But by the same token, the humidity controls how hot it can get. It makes a cap. I don't think there was a single day in Hawaii that ever reached 100 degrees while I was there, but it also rarely dipped below 80, even in the winter. Okay? Humidity will do that. It acts as a temperature buffer. Okay, great. Any other questions? Not necessarily related to deserts, because we're going to talk about that today, but any questions or fun stories or anything? There continues to be a lot of hype about these samples that were found on Mars. We talked about this a little bit not long ago, right? This particular mineral, again, it's not a fossil, it is a mineral that is commonly the waste product of bacterial metabolism. Okay? On Earth, that's the case. We do not know if that's the case on Mars, but it is probably the most compelling evidence that there could have been life there so far. People keep publishing headlines saying, evidence of life found on Mars, right? Or some variation of that. It isn't evidence of life. It's simply the most compelling evidence that there could have been, right? If life did exist on Mars, if there was bacteria on Mars billions of years ago, it is conceivably possible that maybe when the surface died, some of that bacteria continued to live and propagate below the surface. We are a long ways from proving that or from figuring that out. First things first, was there life there at all? That's what we're trying to figure out. And again, this is probably the best compelling evidence so far, but until we get that sample back here and can actually analyze it, not sure. But I want to ask you this, what would it mean? What would it mean if there was proven evidence of bacterial metabolism on Mars that's the same as the bacterial metabolism that we see in the fossil record here. What would that suggest? Right. Okay, so let's say that we can prove that there was life on Mars.
That there was a chance that we could inhabit that place?
No. It'll never be easy to live on Mars. What?
There's life everywhere else in the universe.
Okay, that there's life everywhere else in the universe. We already, statistically, chemically, physically, it's already likely, but finding evidence of life, past life on Mars, would put the last nail in that coffin, right? We would know for sure. But I'm looking for something a little more specific, a little more relevant to us. If we found evidence of bacterial metabolism on Mars, similar or exact to the type of metabolism that we see here, what does that suggest?
Something from Mars landed on Earth.
Did you hear that? Say it louder. Say it prouder.
I don't know how to explain it, but like a meteor or something.
A little louder and prouder.
Like a meteor from Mars that collided the free with Earth.
Something from Mars went to Earth? What? If something from Mars containing that bacterial life came to Earth billions of years ago and that life survived, is that where life started here? Are we Martians? Are we Martian colonists that evolved on this planet for billions of years? We call this concept panspermia. There are two major fields of thought when it comes to the origin of life, right? Biological evolution of life here on Earth. It started here, and here it continues. And panspermia. Life started somewhere else and was transported here. Never evolved here. Never began here, I should say, but has continued to evolve here. What a fascinating concept. Or vice versa, perhaps. What if a piece of rock debris went from Earth to Mars? And that's, in fact, a failed Earth colony. One that died out before it could go further than bacteria. What an interesting thought, huh? We'll find out someday. We'll find out. Hopefully in 2035 when those fossils come back. Or samples. I shouldn't call them fossils yet. When the samples come back and we can do a deeper analysis, we'll be able to tell for sure, is it bacterial in origin? Right now, it's very strong evidence that it is. There are a few other ways you can make those sort of mineral signatures, but they typically require the presence of some other things like various acids that we have not found evidence of as well. Right now, the most compelling case is that it is in fact bacterial in origin. But until we get it back here and can check it, it's simply the most compelling hypothesis. All right? What exciting times we live in. By the way, we talk a lot more about panspermia and the origin of life in 1404. I think most of you are signed up for that class in term 2. We're going to have a good time with that. All right. So let's talk about today's lecture. What is a desert? Someone tell me what a desert is.
Somewhere where
A
it's
place with
dry
low
climate.
moisture.
Hold on. Start here. A vast land of sand. He wants to rhyme today.
Somewhere with low rain.
Low rain. Ooh, okay.
Somewhere with a low climate.
Low climate. What do you mean by low climate?
Dry.
Dry. Okay, so a dry climate. Low rain.
I said somewhere with like low humidity or like moisture.
Low humidity or moisture. Man, we're doing great. Okay, well, let's talk about that first comment. Somewhere with a lot of sand. Is the sand required for a desert? Do we have a lot of sand here? We have some. Would you say that it's everywhere? Would you still call us a desert? Right. We typically refer to where we live in the world as a desert, right? Do we agree that this is a desert? Do we agree that this is a desert?
Yep.
So apparently there is some degree, some interval of climates within which we would consider something to be a desert. So where do we draw that line? How do we define something as a desert?
If it has a lot of moisture, then
Okay, you guys keep coming down to this thing. Moisture, rain. Perfect. Okay? What does dry mean? What is the meaning of the word dry?
Doesn't
Right. It's very difficult to actually throw a measurable definition on what dry means, right? Is Odessa drier than the Amazon rainforest? Is the Sahara drier than Odessa? Yes. Dry is a very relative term, can't really be measured. There is another term called aridity that we prefer instead of dry. Okay? So what do I mean when I say that deserts are dry or arid? Okay? It's any area in which there is a water deficiency. What is a deficiency? A lack of. In what situation would water go away? Okay, a drought is when you get way less water than you should, but where is the water that is coming in going? Huh? Good. Some of it's flowing away in groundwater. What else? Evaporation's a huge one. Seeping into the groundwater, evaporating back into the sky, running off in rivers, things like that, or being pulled away and used for irrigation, right? Remember we learned about the Dust Bowl, right? If you use it a lot for agriculture, you'll deplete the water in the area, right? So wherever there is a water deficiency, the aridity increases. Okay? So when yearly precipitation, that's this P right here, is greater than or is less than loss from evaporation, evaporation in this context meaning any way that water is lost, but evaporation is the largest one, okay? When you have yearly precipitation being less than yearly evaporation, our climate is what we call dry or arid if we're using the proper term, okay? Now temperature has a big role in this. It's not the only role, but it has a big role. Why?
Because it can cause the water to evaporate quicker.
Yes, higher evaporation, or excuse me, higher temperature, more evaporation. That's a huge factor there, okay? So in general, when we're talking about arid environments, for today's purposes anyway, we're going to separate into two categories. You've got your deserts, which are truly arid. There's a high difference between the amount of evaporation and the amount of precipitation that takes place. Or steppes. Steppes, there is less of a difference, still noticeable, still way less precipitation than you should have to have a thriving water-filled environment. And usually these happen at higher altitudes. These usually occur at altitudes that are high enough in the atmosphere that liquid rain is typically not as common instead of temperature being the main reason. Okay? Elevation versus temperature here, right? So let's talk about the places around the world that we find deserts. Okay? We have low latitude deserts. Low meaning it's. Do you guys know how latitudes and longitudes work?
Like shows the place on like exactly on the road.
Right, they're coordinates. Remember that. Coordinates come into play for Lab 5. Not lats and longs, different types of coordinate systems. But you get the idea, okay? But 0 degrees latitude is the equator. You familiar with this concept?
Oh yeah.
So when I say low latitude, I'm not meaning low down here on the planet. I'm meaning low numbers, which means closer to the equator. Because we go 0 to 90 all the way up here. Well, higher than that, but you get the idea. And then 0 getting larger down there, south. So low latitudes, close to the equator. In this case, along what we call the tropics of Cancer and Capricorn, right there. Okay? Cancer and Capricorn being constellations. Okay? That's what they're named after. So, tropics of Cancer and Capricorn. And look, the Sonoran, the Chihuahuan, the Sahara, the Arabian deserts right there along the Tropic of Cancer. Right here. The Namib, the Kalahari, the Great Sandy in Australia. All of those are along the Tropic of Capricorn. What's happening here? Well, I'm going to explain it in a minute, but for now, let's just say it has to do with the flow of air. I'll show you about that here in a second. Then you've got your mid-latitude deserts, the ones that are higher above or below those tropics, okay? The Great Basin, the Mojave, the Turkestan, the Gobi, okay? The Patagonian Desert, mid-latitude deserts. And then you've got your polar deserts. What do I mean by a polar desert?
Cold desert. It's a ice desert.
Instead of hot, it's cold. How does that make sense with what we've described the definition of a desert to be?
It's
I'm not saying you're wrong. I'm just asking for an explanation.
It lacks heat.
Hold on, let's let...
it's has a water deficient, whatever it's called.
Deficiency.
Yeah.
A water deficiency, but we're talking about Antarctica. Is there a water deficiency in Antarctica? I mean, isn't it covered in ice and snow? Gavin, what do you think? Ah, there's the kicker. There is a liquid water deficiency. Can anything grow using just ice or snow? No, it's got to melt into water. So if my ice never melts, there's no liquid water. Do we have a precipitation deficiency? Yes! Regardless of temperature in this case, the amount of yearly precipitation is still way lower than the amount of evaporation. We have a polar desert. Okay, so polar desert, polar desert. Make sense? Great. Great, great, great. It's only Tuesday, isn't it? We have a week ahead of us. I know, it's great. All right. Let's talk about those low latitude deserts. Huh? You think this week will go by fast? Man, I hope so, brother. Should I tell you a joke to get the energy a little higher? All right. What did the green grape say to the purple grape? Breathe! Thank you. There's my ba-dum-tsh guy. What? Oh, you didn't get it? You remember this goes on YouTube. What is the joke? What does it mean? Yeah, what happens when you stop breathing? So the green grape said to the purple grape. Come on, guys. My jokes are not that complicated. They're dumb dad jokes, all right? All right, let's talk about low latitude deserts, all right? So, what causes these low latitude deserts that occur along the tropics of Cancer and Capricorn? This comes down to this little thing that we've already learned about several times called convection. Someone explain convection to me again.
It's when the water, it like goes to the top, or like the.
Keep following your thought. Work it out.
So like the water particles, it goes up.
Okay, water can go up. Under what circumstances would water rise through other water? Why would hot water rise through cold water?
Because the heat rises.
Why does heat rise? Aaliyah? Expansion of the water, which does what? Expanding the molecules, or the space between the molecules, does what to the substance? We're not changing the mass. We are changing something else, though. The volume, exactly. Mass stays constant, volume increases, more buoyancy, hot stuff rises, right? Bingo. Good job. Air does the same thing. Hot air rises. Have any of you ever lived or currently live in an apartment complex? I've lived in so many you would not believe. Okay? Why is it more beneficial in wintertime to be on the second or third story? Because your neighbors, your downstairs neighbors, hot air is rising through your floor and you pay less electricity. They're basically paying part of your electrical bill. Okay? Now, this has been a known fact for quite a while. A lot of apartment complexes will actually take that into account and balance electrical bills accordingly. But it's still a known factor. Okay? Some portion of your neighbor's heat, your downstairs neighbor's heat, is going to rise into your apartment. Okay? Hot air rises. Where do we have the hottest air on our planet? The center being called the equator. Thank you. The hottest air is at the equator. Why? Because the equator represents the transect around our planet. Let me pull up my globe here. The transect around our planet, which is always facing the sun. If the sun is over here and our Earth is spinning, the equator is at any given point along our planet, which is facing the sun, along our spin and along our orbit. Meaning that the most energy is blasting through our atmosphere. I don't know why my camera didn't follow me. Blasting through our atmosphere and hitting the equator the strongest. More heat, more hot air. More hot air, less volume, or more volume, less density, more buoyancy, hot air, go up. Cool. That's half of it. What happens next? We talked about convection when it came to the mantle. The same physics are at play here, my friends. What happens next? Yeah, you may. Why does the air turn cold? You're right, but we missed a step. The air has to turn cold first. Why? We're not far away from the equator yet. The hot air has simply been rising.
It turns cold because the higher the elevation, the colder it gets.
Bingo!
Then the air gets cold and sinks back down.
Yeah, the higher the elevation, the colder the air gets. The colder the air gets, what happens to its volume? It gets greater, and as it gets greater, it gets denser, and as it gets denser, it falls down. But it's still getting shoved by the hotter, warmer, rising air beneath it. And so it either gets shoved north of the equator or south of the equator. And as it gets shoved either north or south, it continues to cool off and falls. Eventually what happens is this cool air is going to start precipitating out all of the water it held. Higher or less dense air has a greater volume. It can hold more humidity. As you start to shrink or reduce the volume of your air, it cannot hold that humidity. That humidity turns into clouds. Those clouds precipitate out rain. So that's why it is almost always raining near the equator. The cooling air above the equator is dropping all of that precipitation. The further north or south your air goes, the more rain it is losing. The more water it is losing. It is becoming drier, so that by the time it actually reaches the Tropic of Cancer and the Tropic of Capricorn, you have cold, dry air. Perfect to make a desert environment. There's not enough moisture to bring consistent rain. And so you get deserts on the continents in those locations. Are you following the logic here? Yes? Is there anyone who is not? Because I don't want anyone to be left behind here. Or do we all understand the concept of low-latitude deserts being made through air circulation, air convection? Yeah? Great. So let's talk about what makes those mid-latitude deserts then. There is a little bit of the air factor here as well, but there are a few other circumstances that can cause the creation of a mid-latitude desert. Okay? First of all, when you have an extremely large continent, okay, do we have an extremely large continent on our planet right now? What is it? Eurasia. Not my Asia, Eurasia. Yeah, you may. Yeah, thank you. That was another bad joke. Okay? No. Eurasia, a combination of Europe and Asia, soon to be joined by Africa. Africa is slowly closing the Mediterranean Sea between itself and Eurasia, and eventually it's going to join forces there, and we'll have a new megacontinent. Can't call it a supercontinent yet. For something to be a supercontinent, it has to contain at least 75% of all of the Earth's landmass. It will not. That will be somewhere between 50 and 55% of the Earth's landmass if you're including Antarctica, which we do. So it's not a supercontinent. It'll be more of a megacontinent, okay?
So what's like the highest landmass so far? Like the
What's the largest one right now?
Yeah.
Eurasia. Yep, Eurasia is the largest landmass right now. And then once Africa joins it, it's going to be even bigger.
what if Australia joins it too?
Australia eventually will join it. Australia is on its way. India and Australia are riding the same momentum. India already joined the party by slamming into South Asia, technically. Eventually, Australia is going to join that party as well. It's going to smash itself. It's going to smash Indonesia and Micronesia between itself and Southeast Asia.
So then how much of that is that going to be?
It still won't be a supercontinent. Theoretically speaking, in between 250 and 300 million years, some models predict that South America and North America will join where the Gulf of Mexico is right now. So South America will move north, North America will move south, and then they will collectively collide with Western Europe and Africa and make a brand new supercontinent that someone's really inventive labeled Neo-Pangea. Very clever, isn't it? Yeah, it's a great name. Speaking of Pangea, though, what do we know about Pangea? What was that? Yeah, it was a supercontinent, right? It didn't include all of Earth's landmass at that time. There was a fair amount of islands that weren't part of that. But it included most of it, the majority of the landmass. Okay? Yeah, you may. So, Pangea, the inside of this big continent, mostly a desert. Mostly desert conditions. Why would we have large deserts inside of continents, big continents?
Farther away from the ocean.
They're so far from the ocean. Yes, exactly. By the time the air that was over the ocean reaches the interior of the continent, it's rained out most of its water. And so only that cold, dry air makes it that far inland. That's what makes the Gobi Desert. This whole area out here is really dry, but this area in yellow is what we call the Gobi Desert. So far inland and north that very little, the winds usually go like this, okay? They're going like this and like this, okay? Very little of it actually makes it that far inland. So we get interior deserts. By the way, another note about Pangea. Not the first supercontinent. Do you know that? There were many supercontinents before Pangea. Again, something we learned in 1404. Also not the largest.
How is that?
How is that? Yeah. There was a supercontinent that existed before that had even more landmass. Yeah. Pangea was the last supercontinent we had, though.
So it's possible for a continent to like break down so much that it like disappears or whatever? Or, like,
Oh yeah, tectonic plates are constantly being made and destroyed. Divergent plate boundaries are adding mass. Convergent plate boundaries are taking mass, shoving it back down into the mantle. Now, in general, it is a general rule that continents get larger over time. But that also has a lot to do with sea level, right? Sea level and how thick my continents are as well. What's the material they're made out of? How dense is that material? How low does it sit in the mantle? There's a lot of factors that go into that. Okay? Yeah?
so as like the glaciers start to melt,
Yeah, as more and more of the Earth's ice melts, like we learned last week, right? As more and more of the Earth's ice melts, sea levels rise, we lose land mass. At the current rate, sea levels will have risen about 10 feet by the year 2100, and then potentially 100 feet by 2200. That's at current trajectories. Obviously, as we continue to alter Earth's climate and as temperatures continue to rise, that's only going to get worse. Yeah.
You know how like AI is run off of water?
I do not know how AI is run off of water.
Well, they run off of water and they use the ocean water. If they use enough ocean water, they'll stop the ocean from rising.
Not that dang much.
AI is not run off of water.
Our teacher told us that.
Are you talking about water-cooled systems?
Yeah.
That's not nearly the same thing. A water-cooled system is when you have to cool off a PC somehow, right? You know how when you turn on your laptop and you play a game or something, the fans go crazy? It's blasting heat out from itself. More efficient and more effective than a fan is a water-cooled system. High-end gaming PCs have water coolant systems in them, and they perform much better. So a server that utilizes that is, I guess I should say, the brain of an AI is going to be water-cooled. They don't run off of water. Okay? They require water to cool down their servers. If you flip that off, the servers burn up and your AI dies. But AIs run off of electricity, just like everything else digital.
They said they use like billions of gallons of water.
They do, because these you should see some of these servers, guys.
What if they just use the ocean?
To provide the water? Well, the ocean has salt in it. Yeah, salt is going to clog up the tubes that they use to cool down the systems. You can't use salt for that. You can't use salt water for that. Good thought. That's a way of trying to utilize something we have in plenty, like salt water, for a problem. So I like where your head is going with that, but it's not the solution. There is a way, though. Yeah?
You like run it through a filter before running it through the PC?
Okay, this is what I was getting to. There is a way to remove the salt. It's called desalinization. Desalinization, right? Okay. So you effectively evaporate your water or use some other chemical to remove the salt, okay? Evaporation is the simplest technique, though. And then you get a whole bunch of fresh water, but then you have a whole lot of salt. What do you do with that salt? You have to store it somewhere. Can't put it back in the ocean. We don't want the ocean to get saltier, right? There are desalination plants all around the world, but there need to be more. I honestly think that the best solution to our freshwater shortage issue that we're going to see coming up is increasing the efficiency and cost effectiveness of removing salt from seawater and then taking that around the globe. Out here in the middle of, the United States, West Texas, where we don't have access to a convenient source of water if ours runs out, we should have a big old pipeline that goes from the ocean, desalination plant out here. That's what we should be building pipelines for. Okay? But again, that's a personal thing. How did we get on this subject? We were talking about AI. You brought up AI. Right, okay. Water cooling systems. That's what they use. Now, the other way that we get mid-latitude deserts is through what is called a rain shadow effect. A rain shadow desert is when humid air runs into a mountain range. Can air move through rock? No, it cannot. So where does it go? It hits the mountain and then goes up. And what happens as we go up, my friends? You cool off, yes. So when you have a tall mountain range and your air runs into it, it goes up. As it goes up, it cools off, rains out most of its moisture on this side of the mountain, goes up over the mountain, and only cool, dry air goes to the other side, and you get a rain shadow desert on the other side of your mountain. Who can tell me where this is in the world? This is Chile. right? If you ever plan on going to southwestern South America, bring a sweater. I hear it's chilly. Thank you. All right. Yes, this is Chile. What do you see? Describe what you see.
It's all brown and then it's white.
It's brown and some white. Those are glaciers on top of. Huh?
Mountain.
Mountains. Yes, there is a mountain range here. You know what we call it?
The
Yeah. The Andes. Thank you. This is the Andes mountain range, right? What is it doing? What do we have on this side of our mountain range? What rainforest is this? This is the Amazon. And on the other side of the mountain range? Desert. Dead. Barren. What is causing this juxtaposition?
Rain, shadow,
Yes, it's a rain shadow desert. Remember, this is in the south hemisphere. So the prominent wind direction is coming from the east here, right? So as all of this wind is moving out of the Atlantic and going over here, it's dropping a whole lot of rain out here that's making this rainforest, hits that mountain range, climbs, cools off, rains out, such stuff. Cool, dry air makes it to the side. We have a rain shadow desert, even though there's an ocean right there. It's right next to the ocean. But there's a desert because it does not get the rain. Okay, rain, shadow, desert. And here is a graphical representation of that. Prevailing winds come over here, rain, 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 rain. Cool, dry air makes it over here. Very little vegetation. Yes?
Is that how Death Valley is? The rain shadow?
Death Valley does experience a rain shadow effect, but that's not the only reason. There are a couple of factors for why Death Valley is the way it is. Death Valley, by the way, for anyone that doesn't know, is the hottest place in North America. I don't think it's the hottest place in the world. I'm not sure about that though. It's the hottest place in North America. Anyone want to Google that for me real quick, by the way? What's the hottest place in the world? How hot is it? I believe that the highest temperature recorded in Death Valley was like 127 degrees or something.
Death Valley, California.
Death Valley is the hottest place in the world? Does it say what the highest temperature was? 130? 134. Wow, it was even 7 degrees hotter than I thought. Yeah, 134. Oh man, what an oven.
It was 57 degrees Celsius in 1913.
57 degrees Celsius. It's given to me in that European designation.
How did they survive?
How did they survive? Well, a lot of people don't live out there. Yeah. There's not a whole lot of people that live out there.
What would happen if they did it?
You better have air conditioning. Yeah, you don't survive in that without air conditioning. The coldest temperature that I've ever lived in is when I was doing night shifts in the oil field, the Bakken oil field in North Dakota, Williston, North Dakota. I was doing night shift in negative 40 degrees. Yeah, that's frostbite in 30 seconds on exposed skin without wind.
Did anybody ever get like frostbite?
Oh yeah. We had incidents like that. Every now and then, because drug abuse is a huge problem up there in the oil field, we would find people that had crashed out because they had taken a bad batch of something and they had not bundled up well, and so they froze out on their shift.
In a block of ice?
No, they weren't in a block of ice. What are we in, Looney Tunes? No, they just died because it was cold. They froze. Block of ice. Yes, we turn into ice sculptures when we freeze. That's what happens. Now I want to draw your attention to something here. Rain shadow deserts form because of mountain ranges. Interior continental deserts form because of the size of a continent. What do both of these have in common?
Yeah, they travel over distances.
air connection.
Although the low latitude deserts that form, yes! It all comes down to tectonics, my friends. It always does. Okay? Tectonics made those mountain ranges. Tectonics made continents collide and make massive areas of land. Tectonics are what's making land be present at the tropics of Cancer and Capricorn. If there was no land along those latitudes, there would be no deserts, right? All of this comes down to tectonics. An understanding of tectonics is essential in so many things. And you know what? What did we figure out about glaciers last week? You got to have tectonics for that too, to make the mountains high enough in the atmosphere to be above the snow line, right? Tectonics. Any questions before we move on? No? Okay. All right, so in a desert, there is still weathering and erosion happening. Let me ask you a question. Do you think that if an area receives 1 day of rain a year and has no rain but a lot of wind for 364 days out of the year, which force provided the most weathering and erosion? Clearly it's the wind, right? Except it's not. It's not. The 1 day of rainfall actually provides more weathering and erosion than the entire rest of the year with wind. Why? Water is so much thicker, so much more viscous than air. Air does something, right? Here, when we get high enough winds, we get sandstorms. It's been a minute since we've had one. We get usually 1 or 2 a year, right? Where a big cloud of dust gets blown in. For some reason, I'm usually at Walmart when this happens. I don't know why. It's just my luck.
I mean, I always see it like cop cars and so getting arrested at a Walmart parking lot, so.
I promise I've never been arrested at the Walmart parking lot. But for some reason, I'm walking out of Walmart right as one of these things is blowing into town. And then the next thing I know, I can barely see anything in front of me, and I'm trying to push a cart with my children in it across the Walmart parking lot. And I'm like, please, please, please don't let anyone be driving down this lane, right? Just my luck. But anyway, so yes, wind does provide weathering and erosion over the course of all this time. But the little bit of rainfall that happens can carry and move and break up sediment so much more effectively that it still makes up for the vast majority of weathering and erosion. Okay? When we get rainfall in the desert, all that water will run through what we call ephemeral water bodies, ephemeral streams, like this one. Here in this picture, you can tell that there's kind of something there, but it just kind of looks a little bit different from the landscape around it until you realize when it's full of water, that's an ephemeral stream bed. It's dry most of the year, but when it rains, it gets filled with water. That's what it looks like almost every other day of the year. We call this an ephemeral stream bed. There are also, there are different names for these in different languages. A wash, you may have heard that term before, or an arroyo, wadis, dangas, nolas. There are lots of names for these things. Huh? No, it's a wadi. Depending on which culture we're talking about, every culture that's grown up next to a desert or in a desert has some sort of name for these, right? And often those cultures have celebrations. They rejoice when they're filled with water because, I mean, gosh, if it only rained 1 or 2 days a year, how much do you guys like it when it rains here? I love when it rains here. Like, I'll go out and be on my porch. I sleep so well with the sound of rain. Oh, I miss it. I used to live in Seattle. It rained almost every day. I miss it so much.
Do you sleep with like the rain noises?
I don't. No. No. I don't need that to go to sleep. No. Do you sleep with rain noises?
I don't sleep with any noise.
You don't sleep with any.
Fan, actually.
Okay, a fan. Yeah, so a little bit of noise, right? We usually have the ceiling fan on, but that's only because of how hot it is. Especially this time of year. Yeah. Okay. Now let's talk a little bit more about this wind erosion. Remember, erosion is the transport of sediment. Did you have a question? No? Okay. The erosion is transport of sediment. So we talked about how running water, it has a dissolved load, a suspended load, and a bed load. Well, it's generally true for air as well, except you can't really have a dissolved mineral in your air. So we have a suspended load and a bed load. Suspended load being the particles that are small enough that the energy in your moving air, aka wind, can pick up that particle and move it. Those dust storms that we see blow in, that's all suspended load. Bed load, just like with water, is what's getting pushed and tumbled across the surface, whatever surface we're looking at, whatever surface we're talking about here. Okay? So in this case, this dune, the side of this dune, with the sun coming behind it, you can see the bed load getting pushed along the surface. It's getting shoved up into the air for a second over this edge before it falls back down on this side of the dune.
I'm not even gonna lie, at first I thought that was the sun.
Oh, you thought that was the sun? I mean, the sun is behind it, which is why you're seeing the light there. But that's all bed load. Probably sand that's getting pushed up over the edge before it falls down on this side. Okay? The movement of this sediment due to wind, the removal of sediment due to wind is called saltation. This has nothing to do with salt. Simply the word for it. Saltation, the removal of sediment from one area to another. Okay? Deflation is what happens as the process of saltation is occurring. So when I say an area is suffering from deflation, that means that it is losing all of the little particles that the wind is capable of blowing away. And eventually all you're left with are the big particles that your wind couldn't move. Okay? We call that a desert pavement. If you've ever gone walking, how many of you have ever been over to these sand dunes? Yeah? When you're walking through the dunes looking for that perfect sledding hill, and you're going between the dunes, you're between two dunes, and all of a sudden you're walking over a bunch of rocks, like random rocks that are just kind of there. That's desert pavement. The smaller particles have gotten blown away from that area into the dunes around it, leaving only the larger particles behind that the wind could not move. If you ever go to Montana, there's tons of this out there. The Montana Badlands, lots and lots of desert pavement out there. Makes for actually really good fossil hunting because the fossils are usually too large for the wind to move as well. All right, ventifacts and yardangs. No, these were not named by Dr. Seuss. Yardang is actually a Pakistani word. Okay? So a ventifact is what happens when you have a rock that is exposed at the surface to the wind's weathering effect. Remember, as the wind is eroding the sediment, so carrying that sediment around, particularly your bedload of sand, it's pushing it along the surface, it's going to sandblast everything in its path, including the rocks that are sticking up out of the ground. So you get this sort of aerodynamic, super smooth, sandblasted surface on all of your rocks that are exposed to that. We call that a ventifact. I have found many of these things. If you pull this up out of the ground, underneath the surface, it's still going to be blocky and jagged, and it's going to look like a dirty rock. But it looks like this beautiful, smooth, sandblasted, polished surface above the surface. And then this is a yardang. It kind of looks like a mushroom, doesn't it? What effect could have caused this?
Water running underneath it.
Are we talking about running water? Wind. Doing what? Blowing what? Okay, so the wind is only blowing down here? Is that how wind works?
That rock was bigger before.
Oh, it was definitely bigger before.
Bigger rock next to it.
There's a bigger rock next to it, and this one felt intimidated and got thinner. Whoa, what happened? Why is this rock formation thinner at the bottom than it is at the top?
Because the larger sediments were hitting the bottom.
Ah, okay. So as the wind is blowing, the suspended load, which is usually, clays and silts and smaller things, does carry some weathering effect up here. But the greatest weathering effect is from the heavier particles getting moved in the bed load, the sand-sized particles. So it's getting sandblasted at the bottom of this thing, right? Actually, it's getting sandblasted that way. How can I tell? There's more weathering on this side than there is on that side, right? And the shape here has become aerodynamic that way, tapering off in that direction. Like an airplane wing. Have you ever looked at the cross-section of an airplane wing? We build our airplane wings so that the thicker end is facing in the direction the airplane is traveling, and it thins out, tapers out behind the airplane, because that is the most aerodynamic shape. Yeah? You what? Yes, of course. So yeah, that's why he's taking on the shape. Wind is going that way. But yes, more weathering at the bottom because it's getting the sand blasted up there and much less weathering occurring up there. All right. When sand, this bed load, gets moved around the surface, eventually it's going to get piled up. We have a special name for these piles of sand. What do we call those? Yes, they are sand deposits, but what do we call those? Huh?
Dunes, or sand dunes.
Dunes. Yes, they are dunes. Have you guys seen the Dune movies?
Yes.
Timothy Chalamet and Zendaya? Oh, they're so good. I love those movies. I love the books, but the movies are fantastic. Right? I'm so excited for the next one. I mean, there are 2 so far. There's a 3rd one coming out next year, I believe. Anyways, so these dunes move in the direction that the wind is blowing them. They actually migrate across the surface. Matter of fact, migrating dunes are a real problem for some communities here in the West. They will actually push their way. The wind will push these dunes across roads, into the middle of town. There are some towns where they actually have to use snow plows to clear away dunes that have blown into the middle of the road during the night. Right? They can be a real problem. Your dune has a couple of different parts to it. Okay, so you've got your slope right here, and then this steeper side, we call that the slip face. That is your slip face. So the wind is blowing sand up this gentle slope here, and then as it reaches the peak over here, this pinnacle, it collapses down the other side. Slip face. Wind is the driving factor on this side. What's the driving factor on this side?
Jagged.
What's the force causing motion on this side of the dune?
Oh, gravity?
Gravity. Wind's pushing it up the hill. Gravity causes it to fall down the other side.
So that's why, like, sand dunes have so weird shapes, like a bunch of off random shapes.
Oh, well, let's talk about the sand dune shapes. Okay? So your normal characteristic, when you think of a sand dune, you think of this shape. Dune is called a Barken dune. And it has this crescent shape, like that. Yeah, it kind of looks like a horseshoe, kind of like a crescent shape. In the side view, it looks like this. Slope, wind's pushing it up. Slip face, gravity's pushing it down, pulling it down. Okay? Why does it make that horseshoe crescent shape?
Because it's like the wind is like pushing it and the lighter stuff goes further.
So you think it has to do with the mass of the objects being pushed?
Yeah, kind of.
Not so much that.
Like, just really strong wind.
Regardless of the strength of your wind. Actually, if you have a very strong wind, you'll get a different shape entirely. I'll talk about that next. Yeah, you may. Any ideas over here, actually, for why our Barken dunes make that crescent shape? Doesn't have to do with the size of the sand particle. We're assuming uniform sand size here. This would happen in that case or regardless. Nature will always try to do things with the least amount of energy possible. There's a clue. Any other ideas?
Whenever light wind it'll push it up against it, but it's not strong enough, so kind of just forms a ramp, kind of.
Well, yes, it has made that ramp, right? This is the side view of our dune. There's a ramp here. where is the least energy required to move the sand?
On the sides of it.
On the sides of it. The wind has to push sand all the way up here before it can fall down that slip face. Or the sand can move this way. The sides of my pile of sand move faster than the middle does because it takes less energy to move sand along the sides. And yet, wind doesn't choose. Wind just blows. And so while the sand here and here is moving faster, there is still sand getting shoved up here. And so while the sides are moving at a faster rate than the middle is still moving, and thus we get a crescent shape where the sides move out in front of the middle. Does that make sense? Great. Wonderful deductive reasoning. Huh? Yes, you were right. Yeah. All right. So now, what about an environment where we have even more sand? A lot of sand. We call these sand seas. Okay? Places like the Sahara, where the sand is so deep that you almost can't get through it. Really, really deep. We get what are called transverse dunes. Okay? What does that look like?
Like waves.
Oh, yeah. It does look like waves, doesn't it? What's happening here?
Is it like that thing where it's like the wind pushes the settlements from the what's it called? It's the it pushes the settlements off the bed and then it like drops it back down and picks it back up, drops it again.
No, that's not what's happening, but I appreciate the thought and the guess. When I have a whole lot of small particles and I inflict them with some physical force, they are going to respond, correct? Regardless of the size of the particle in question, the physics are still the same. Consider molecules of water under the influence of wind. They are going to whip up into a wave. We see this in the ocean. Consider grains of sand under the influence of wind. What are they going to do? The physics are the same. The forces are the same. It's only the size of the particle in question. You are going to get, essentially, waves of sand, given enough application of force and time. These don't move anywhere near as quickly as a wave on the ocean does, but particles of water are significantly smaller than grains of sand. Takes a lot more energy over a lot more time to move these waves. Why do they look like waves? Because that's basically what they are, which is why we call these sand seas. Okay? They are under the same physics and the same forces as the waves in the ocean, and they respond similarly, just all over longer timelines. All right? So what if I have an all right amount of sand, but not as much as I would to get transverse? We get Barkanoid, which are essentially a combination of Barkan and transverse, where you still have these kind of waves, but they look like a whole bunch of side-by-side crescent shapes. Okay? Like a bunch of Barkans came side to side, which is basically what happened here. They combined sides and made these dunes, these Barkanoid dunes. Okay? So lots of sand, little amounts of sand, moderate amounts of sand. Now let's change up the wind conditions a little bit. Longitudinal dunes still have that kind of crescent shape, but are stretched real thin and long, like that. Why? This is actually something that came up a little bit ago. The wind is strong. When my wind is really strong, the sides get pushed out way further than the middle does. And so we get these stretched out longitudinal dunes. Okay? What about parabolic dunes? In a parabolic dune, we still get our crescent shape, but now the crescent is pointed towards the direction of wind instead of away from it in a Barkin or a longitudinal dune. Why?
Because of the water nearby.
No? Something else is doing this.
Oh, maybe because like the grass. Because the grass, like the smaller stuff is like staying like with the grass.
By smaller stuff, what do you mean?
Like the smaller amount of sand,
And the smaller amounts of sand are where?
like in the grass.
Huh? The sides. So for the same reason that we get a crescent shape in a Barkin dune because the sides move faster under the influence of wind because there's less sand there. In a parabolic dune, where the sides, which contain the less sand, are being held together more effectively by vegetation, this time they move slower than the middle of the dune, which has way more sand and less vegetation. And so the middle of our dune moves faster than the sides, making that same crescent shape, but flipped 180 degrees. Bless you. You following me? You picking up what I'm putting down? Smelling what I stepped in? Good. Oh, I smell it. All right, and then we have star dunes. In a star dune situation, we have multiple crescent shapes. Are my labs okay over there?
Yes, thank you.
Okay. We have multiple crescent shapes in different directions. What would cause that?
Wind from all directions.
Yeah, we get wind from multiple directions. And so we have wind blowing one way, maybe this way here, and then this way that time, and then this way at that time. This can occur through temperature variation through different points of the day. This can occur seasonally, where it'll blow this way in the spring, and this way in the summer, and this way in the fall. There are many situations that can cause this to happen. If you ever go to the Monaghan Sand Dunes, look for star dunes. There's a few of them out there. Okay? Okay, any questions about dunes? So that explains what happens to the sand. But sand isn't the only particle being moved here. That's the bed load. What about our suspended load? What about the smaller particles that are getting carried in the wind? We call that loess, L-O-E-S-S, pronounced loess. Loess can get transported very far. Look at this satellite image. Here is the west coast of Africa, the Sahara Desert. What's getting blown across the Atlantic right here?
Sand.
Look, not sand, loess. Look at all that loess getting blown across the Atlantic. And where's it landing?
North America.
Well, North America is up there.
That's East America.
Central America.
East America. Where's East America?
Central America.
Oh, wait, that's over. Never mind.
The Gulf of Mexico.
Yeah, look at this. Well, there's the Gulf of Mexico. Most of this stuff is landing over here.
Like between Chile and Mexico.
Well, there's Cuba, right? Here is the south coast of Yucatan. Panama's down here. It's all getting deposited right here along northern South America.
It's over here.
What is what?
The east is over here.
Yeah, I know the east is over there.
Oh, okay, I thought you were saying where.
No. There is no place called East America. That's what I was making fun of. No, Eastern North America is over there. All the way up there. Actually, it's right here. But yeah. It was rhetorically mocking. Right? Okay, but all this dust is getting deposited over here. Can be a source of air pollution. Okay? The more dust that gets blown over here, the less quality air they have over here. But at the same time, it's depositing soil or dust that can be used later for soil. Turns out that this dust is actually really good for soil. You can use it for a lot of stuff. Okay? It gets deposited as very dense, thick, almost brick-like deposits, and it's difficult to dig into, but once you do, it makes very, very, very strong cliffside dwelling. Okay. Loess makes for very, very good growing soil. Fantastic for planting things in. Let me tell you a story. Very, very long time ago, a few wandering migrant tribes in East Africa found a river. This river is what we now call the Nile. The Nile River is filled with soil that gets blown into it from the Sahara Desert, this loess. This loess, which has been reduced to this fine clay-sized dirt, has never once been utilized by a plant in the Sahara Desert. There are barely any out there. So all of this dust that gets blown into the river is prime, perfect, 100% usable by plant life. And it has not been reduced at all. Yeah. And so plants live in plenty and healthily and forever. And there's just so much plant life along the side of the Nile. So these people, they find the Nile River and like, oh, wow, stuff grows really well here. It's been a long time since we found a place where stuff grows this well. So they decide to stay a season. They grow some crops. They decide, you know what, we should stay another season. So they do. And eventually they decide just to stay permanently. They make a settlement. One settlement becomes two. Two settlements becomes four. More and more people living along the side of this river. As their crops begin to be more and more successful and they grow them in larger and larger quantities, they start trading with other civilizations around them to the north, to the west, to the east, to the south. And they start growing in wealth and power and influence in this area. Eventually, they form an empire based entirely upon their agricultural prowess. And then they turn into a highly militant empire that is backed by the enormous amounts of food that they can grow for their armies. We now call this empire the Egyptian Empire, and it lasted for 5,000 years. Purely because of the simple fact that the Nile River soil is wind-blown loess from the Sahara Desert that is perfect for growing plants. That's how they started. That's how they lasted. Yeah? How did they end? How did they end indeed? The Egyptian Empire saw several rise and fall moments. When I say that they lasted 5,000 years, I mean that like their civilization collapsed after like 3,000 years, and then they built themselves back up, and then it collapsed again 1,000 years later, and then they built themselves back up, and then it collapsed again in 5,000 years ago, or not 5,000 years ago, but after 5,000 years. That last time was mostly because the Romans invaded them and kind of messed them up. They clashed with the Romans for quite a while. They were already in the middle of a cultural and societal collapse. Rome and a few other aggressors and a few other things that happened, a few natural disasters as well, some droughts that happened, were kind of the last nail in that coffin, so to speak. Yeah. Anyways, so a major part of human history, human cultural and societal development as a result of a geological phenomena. That's cool. We've already found a few of these in our class. All right, so there are a few other geological things you should be aware of in deserts. Mountain ranges exist in deserts. Stuff is continually breaking down, mostly chemically, as a result, or through gravity, right? And then whenever there's rain, all of that stuff that breaks down throughout the year gets flushed out of the mountain range, downhill, and gets deposited as what? What do we call these? They're alluvial fans. Yeah, these are alluvial fans that build up at the base of the mountains that really only get fed by sediment every time it rains a few times a year here in these situations. Then we can get a playa. A playa is where a body of water used to exist, but is now dried, leaving the dehydrated, the dried out bed for that body of water. You ever drive through Utah? So much of Utah is all playa. Okay? Wear sunglasses. It's blinding. Usually covered in layers of salt and gypsum, which are evaporate minerals. But I know what you all were asking. Wait, Professor Hart, what happens if the volcano gets incorporated into a desert? Oh, well, don't worry. I have that answer for you. We call that an Inselberg. Okay? Whenever a desert evolves, forms around a volcano, it kind of turns that volcano over time into this sad, kind of mushy, vaguely volcano-shaped mound. It's got dunes. Look, it's got dunes blown up all against that side, but it's also acting as kind of a shadow. There are no dunes on this side because this is blocking the dunes from moving past it, right? But they're all getting piled up on that side. Inselbergs always they kind of look like a Hershey's Kiss that you put in your mouth and sucked on for a second, and then you pulled it back out, and now it's just kind of this gross, half-melted Hershey's Kiss.
So what if like a volcano like erupted in the desert?
They do. They can.
Would it just like make a bunch of glass?
Oh, I see. If the lava went over the sand, it might make a thin layer of glass on the top layer of sand. More than likely, you would just fuse the sand together underneath of it. It probably wouldn't completely melt your sand. Maybe the topmost layer of sand that interacted with it, but yeah. You might get some glass as a result. Yeah?
Any super volcanoes in the desert?
No. The only two supervolcanoes that are active, remember, are Yellowstone. And you guys remember the other one? Not Vesuvius. Who remembers the name of the other supervolcano?
Where's it at? I think I know it. I know where it's at.
Here, let me pull this up. We talked about this in lecture 4. There it is, Mount Tambora. What'd you say? Vesuvius? Oh yeah, super close. Vesuvius in Italy, Tambora in Indonesia, very close. All right, any other questions for me today? That's all I got for lecture. We're going to move into lab time unless there are more questions. Good? Fantastic. Then I'm going to end this recording here. Oh, wait, let's vote real quick. Do you guys want to have an extended lecture session so that we can do exam 2 review on Thursday, so in 2 days from now, and then you can have the exam over the weekend, so Thursday afternoon through till Sunday at midnight, I think is when I cut it off, okay? Or you can have a little more time to prepare. We have the exam next week. We have the exam review on Tuesday. I open the exam after class on Tuesday. You have Tuesday afternoon, all of Wednesday, and then technically Thursday until we start class to take the exam. Okay, so there's option 1, weekend exam. Option 2, a little bit more time, but midweek exam. Who wants option 1?
What's option 1?
Weekend exam. 1, 2, 3, 4, 5, 6, 7. Midweek exam, but a little more time to prepare. 1, 2, 3, 4, 5, 6, 7. Yeah, we've had, I think there were a few abstentions. Which one would you prefer?
Hey, Liam's back. Ask her.
Aaliyah, do you want a weekend exam or do you want a midweek exam? You want me to present the options again?
No. This is weekend exam. During school days on.
Weekend? Okay. Juliet? This weekend. It would either be this weekend or the middle of the week next week. Who else? Did you vote? I don't think you voted.
I'll do weekend.
Weekend? Okay, well, so far that's 9-7, I think. Who else hasn't voted?
Hey, sir, he hasn't voted.
Huh? I'd rather leave it up to democracy than chance. you know. Midweek? Remy, did you vote? What'd you say? Weekend? All right, everyone has had a chance to vote, right? Okay, one more time. Weekend, raise your hand. Raise them high. 1, 2, 3, 4, 5, 6, 7, 8, 9. Midweek, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm the tiebreaker? Nuh-uh.
Hey, flip for it. Heads or tails?
All right,
Bro, if we get the freaking
No. Okay, at this point, with a straight up tie, yeah, let's flip a penny. Who's got a penny in their thing?
I got a quarter.
Well, there are pennies in these things. It doesn't really matter. All right. All right. We've got George and we've got Virginia.
Bro, I don't even care for her.
All right, so weekend, Virginia. Midweek, George.
Bro.
I like George. It has to be the weekend.
Weekend, Virginia. Midweek, George.
I think I could used to.
What do you mean I gotta do that again? If it lands on the floor, it's not valid?
Bro, cross.
Hold on. Do you guys want me to do it again or keep it? Yeah. You want me to do it that way?
Flip it and catch it, like if we're doing a football game.
Yeah, like that. It's Virginia. Virginia.
It's George.
Oh.
All right, midweek next week.
1 out of 3.
Midweek next week. So we will have our exam 2 review on Tuesday, and the exam will open immediately after that.
Thanks a lot, guys.
So we have until when?
You have come prepared next Tuesday, so a week from today, with questions. Online students, you now have a week to prepare your questions and send them to me before Tuesday lecture next week. Okay? And then you will have Tuesday afternoon through till class begins on Thursday to complete the exam. Then that day, Thursday, we will get lecture 12. Then the next time we meet, the next Tuesday, lecture 13, and then your final exam review the following Thursday, and that's the last time we will meet because the class is over after that, and hopefully you will complete the final exam in time. Yes? Lab exam is going to be, well, if we're doing exam 2 on Tuesday. Really? To make up for it. Oh, an interesting proposition. Yeah, no. This is interesting. You could have the lab exam this week through the weekend.
Oh, yeah.
Or you could have both exam 2 and the lab exam next week. Because next week is technically when the lab exam was going to happen.
We're not unemployed like you, bro.
So do you have two exams in the same week, or do you take lab exam a little bit early to avoid having 2 exams in my class on the same week? Take it early? All right, should we have another vote?
Let's have another vote.
Mister, give us the exam next week and then the lab exam this week.
Okay, so that's option 1. Now that we have established it is set in stone that the exam 2 will be next week. Do we have the lab exam this weekend or pile up exams next week? So option 1, lab exam this weekend. Option 2, 2 exams next week. Hold on. Option 1, raise your hand. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We don't even need to vote for the other one. I'm sorry, the majority already voted for the lab exam this weekend.
Hey, sir.
Yeah.
So we're gonna have lab 1 exam this Saturday.
No. It will open after class on Thursday. Yeah. So your lab exam, I'm going to open it for you after class this Thursday. If any of my in-person students want to take that in class, you can. I have hard copies of that lab exam for you that you can work with. It will be due Sunday at midnight, just like a normal exam over the weekend.
Blaze.
No, just the lab exam. There's only one lab exam. One lab exam. The lab exam covers all of lab 1, 2, 3, and 4 that you have done. So I really hope y'all have completed the labs because you can't really do well on a lab exam that you haven't done the labs for, right?
Identifying the rocks.
Yeah, it's mineral and rock identification.
Oh, that's easy.
I'm definitely going for that.
I'm glad you think that's easy. Yeah. I do? Yes, I have offered tutoring this whole time. And I also have an after-hours tutor that can meet you virtually or in person at the LRC if you are only available after 5 o'clock p.m. Because I don't do tutoring after 5 p.m. That's when I leave to go home. Okay? It's always been an option. It's been an option since day one. All right, any other questions? Okay, so then, again, anyone that wants to take the lab exam in person can stay after class on Thursday and take it. If you need a little extra time, tell your other teachers that you have class 4 right after mine, that you have an exam to take that you want to take in person, and hopefully you can work that out with them. If you don't and you want to come back later in the day, let me know. I can set you up with the lab exam here in the classroom. My online students, unless you want to come to the campus, you have to take it completely online, which you have videos for on the lab exam. Yeah?
Is it mandatory to take it in person?
It's not mandatory to take it in person. You also have access to the same videos that my online students do for the exam. But I also have physical sets of the labs because you guys have been working with physical sets.
Wait, it's all the labs into one?
I remember how to identify rocks.
I guess so just by way of information, there are 12 samples to identify on the lab exam.
Oh, that's why.
Is this one of them? No.
Why would I tell you that?
I know how to identify.
Just freely give you a question.
Break it around and rub it on your hand.
No, it's all of them.
So there are 12 samples on the lab exam. 3 samples from every lab you've done. You've done 4 labs, 3 samples each. That's 12 samples to identify. Okay? And that's the exam. That's your lab exam.
And that's
All right?
it, right?
Huh?
And that's it.
And that's it. That'll be the last identification exercise you do in the class. Bless you. There is one more lab, but it won't be on the exam. You'll have the 5th lab after you take the lab exam because it has nothing to do with identification. That's about maps.
We got this.
Yep, you're going to learn how to read different kinds of maps.
Is that like the mountain behind?
We'll talk about that when we get there. Okay, but everyone's clear on the exam? Okay, lab exam this weekend, exam 2 next week. Cool? This was decided democratically. Well done, everyone. Yeah, democratically. Let the chips fall where they will. All right?